In this tutorial, we're going to introduce you to material plasticity in Abaqus and show you how to set up a simulation to include it. In addition, we're going to perform a restart analysis so you can see how this is done in Abaqus. In a previous tutorial, we analyzed a planar shell or plate bending under the action of a load. The plate in that example was provided elastic material properties, and the load magnitude was such that the maximum stress on the plate was less than the yield stress of its steel material. Now we're going to modify that simulation to demonstrate plastic behavior. The planar shell will be loaded with two concentrated forces of 270,000 newtons each, so that the stress in some regions will exceed the yield stress of steel and the plate will deform plastically. The material used is a generic steel with a density of 7,872 kilograms per meter cubed, a Young's modulus of 200 gigapascals, and a Poisson's ratio of 0.3. The plasticity behavior of steel is represented by the stress versus plastic strain curve displayed here. The plasticity model in Abaqus defines the post-yield behavior for most metals. The data required is the true yield stress of the material as a function of true plastic strain. The first data point corresponds to the initial yield stress, also known as the elastic limit of the material. Hence, the plastic strain value associated with it should be 0. It is important to know that Abaqus expects the data to be supplied in the form of true yield stress and true plastic strain. This is the case in the current example, hence we can use this data to define the material plasticity behavior. In the course of this video, we will also discuss how to deal with material test data that is in the form of nominal stresses and strains, as is often the case. At the end of the load step, we will release the load, allowing the plate to spring back and recover its elastic deformation. The plastic deformation, of course, will not be recovered. However, we will not perform the spring back step in the same analysis as the load step. Instead, we will perform the load analysis as a complete job, request Abaqus to output a restart file, and then use this restart file to continue the analysis as a new restart job from where the previous one left off. Restart analyses are useful because they allow you to add another analysis step to a completed analysis job. This is very handy if your analyses take several hours or days to run, and you don't wish to add the new step to the original model and rerun the entire thing from scratch. It also sometimes helps to run a multi-step simulation in the form of separate jobs with restarts, so you can examine the results of each analysis and confirm that it is performing as expected. Restart files are also useful if your analysis fails or crashes at a particular point. You can try readjusting your loads or constraints and continuing from a particular step or even a specific increment. However, you must request Abaqus to output restart data before running the original simulation, otherwise no restart file will be created. Let's start Abaqus and work through this.